Welcome back, mathletes. We are going to finish up section 2.2. I had to stop the last video because lunch ended, so I'm going to pick up here in kind of the middle of this example about the relation between two lines and their slopes. You probably see where this is going. The first set of lines that we had were parallel because the slopes were the same. We look at the next two lines that we have here. I'm just going to try to separate this a little bit. Next two lines, I'm going to again call them line 1 and line 2. I'm going to find the slopes of each. Slope of the first line is going to be, let's see, -3 over 2, -3/2. And of our next line, we're going to have, let's see, 3 minus 1, 3 minus -1 over 2 minus -4. So we're going to have 4 over 6, and that simplifies to 2/3. So the slope of line 1 is -3/2, and the slope of line 2 is positive 2/3. I'm going to graph these real quick. That first line has a point at -2, 2, and 0, -1. We can use our slope of -3 over 2 to help us get another couple points. If I went from this point down 3 over 2, I'd end up at the other point that's the y-intercept. I can keep going down 3 over 2, just get a couple other points here. Gonna go back up to this one and go up 3 over 2, just get one more, and we have a pretty decent line here. Moving on to line 2, with the point at -4, 1, -4, -1, and 2, 3. Now that slope of 2/3, if I start at one of the points and go up 2 over 3, gets me a nice point in between there. And then I can go up 2 over 3 from either of the two original points, down 2 over 3. Just make sure you're keeping that positive slope when you do that. And I have a good representation of that second line. And of course, we can tell these are perpendicular lines. And we'll just say that line 1 is perpendicular to line 2. This is because the slope of one of the lines, let's just say the slope of line 2, is the opposite reciprocal of the slope of the other line. In fact, I'm going to put that little blurb down here, opposite reciprocals. Hopefully you remember that from Algebra 1. Two lines of opposite reciprocal slopes, we know that they are perpendicular. All right, moving down to an application of slope, rate of change, or the amount that one quantity changes on average relative to the change in another quantity. Just a small example here to illustrate that. We have a giant sequoia tree, 1965, measured a diameter of 137 inches. 40 years later, in 2005, it had a diameter of 141 inches. Now, assuming that it grew with a linear change, we're going to come up with the rate of change here on average over those 40 years. So the average rate of change in this case, I'm going to fix this, is the change in diameter over the change in time. Okay, so the change in diameter was 40 inches. The change in time from the original year, which is 1965, was 40 years. Excuse me, change in, let's get this right here, sorry. Fire alarm today threw me all off. All right, try that again. Change in diameter is not 40 inches. Let's do some math here. In fact, why don't I just write this? 141 minus 37. And then for our change in time, we've got the 2005 minus 1965. I'm just going to put down that 40 years right away. So we have 4 over 40, or 1 over 10, which means 1 inch every 10 years. Okay, so on average, the giant sequoia grew in diameter 1 inch every 10 years. All right. As a simplified rate of change, as a annual or a unit rate of change, we would say it is 1/10 of an inch per year. 1/10 of an inch. I'll keep it as a fraction. 1/10 of an inch per year, or 1 inch every 10 years. And then just for our purposes here, that's where I'm going to stop. We're not going to worry about the 2065 thing. We could come up with a quick linear equation and put in a value to find out what it is in 2065. We'll take a look at that in class.